Hello all, my name is Jacob Jepson. Here today for the Butter Group, we're going over our dynamics analysis. We'll talk about the few components that we're using, the given parameters about those, and how those help us to solve for our outputted force desired. So, to begin, for our analysis, we have three main components: an AC motor, a gearbox, and a conical shredder. And these three components have some given values here. First, for our AC motor, we have a power in of 150 watts and a omega, which is an angular speed output of 10,000 rotations per minute, RPM. That then is transferred through a gearbox to a angular velocity out of that. So a speed reduction and a torque increase, and that output is 200 RPM. And then that power is then transferred to a conical shredder of a minimal diameter of 2.5 inches. And in our gearbox, because we have plastic gears, we used an efficiency of about 70% due to some power loss because of some slop in those gears. So just to verify first, starting with our motor, we know that the power in is 150 watts, so the unit conversion to horsepower shows that our motor purchased is a 0.2 horsepower motor. Our gear reduction, so instead of just gear to gear ratios all the way through, we can just, since they're all combined in unison in one system, we can go from the beginning gear all the way to the exterior gear. And we see that from our angular velocity of 10,000 over that 200, we get a 50 to 1 speed reduction, but also torque increase. So that's ideal for our shredding application. So using our numbers to calculate the torque output, but also that tangential force, which is what we're looking for here. First, we do some unit conversion for our angular velocity out of that gearbox. So 200 RPM to radians per second is 20.94. Then we take that torque output. We take our power input times that loss in efficiency, that 0.7, and then our work output of that gearbox, and get a 5.01 Newton meter torque. So force is R cross F, so we divide by R, diameter over 2 to get that force. So our calculated torque divided by our radius, or half of our diameter, we get 158 Newton meters. Then converting that into American units, we get 35.5 pound force. And that's pretty much ideal for us, just simply doing frozen or refrigerated butter going through our shredder there. Our goal was to roughly get a pound force around 30 to 35, so hitting that 35.5 benchmark is ideal for us, and that is our dynamics analysis.
This here is the outer shell of the Butter Buddy. You can see here on the front faces, we have the openings for the heater and for the grinding unit. And I included a different masses that are placed throughout this to simulate the other components, because we're just looking at the outer shell. But we ran a drop test. I ran a drop test in SolidWorks on this plastic shell, and I went through a lot of the different von Mises stresses, shear stresses in different directions, and this was the worst case scenario. It was the shear stress on the YZ plane. And we can see here that the shear stress is roughly, the worst case scenario is negative 5.62 megapascals, compared to the other end, which is 4.948 megapascals, which is much lower than the shear strength, or the shear strength of this material, PA type 6. The shear strength there is roughly 30 megapascals, so it's a lot lower than the shear stress that we're going to see if this was dropped from a height of 36 inches, which is about the height of the average counter. So if it's dropped off the counter, this plastic outer shell will perform very well and it will not break um, if we make it out of PA type 6. So we can see that here after we did this drop test.
Hello, my name is Damian Morales, and I was in charge of the circuit analysis for the butter project. Right here, we have our diagram. Right here, we got 120 volts on the wall, and that's going to two switches, one for the heater and one for the salad shooter, and those two will flow to ground. As you can see, they're wired in parallel. And the first thing I did was I solved for the current for our heater. We got 4.17 amps, and for our salad shooter, the current is 1.67 amps. And they're both on. It's pulling 5.84 amps. So normal power outlets are in for 1800 watts, and what we're using is only 700 watts, so we're under that. So we're not going to be tripping any breakers. So I decided to use a factor of safety of 1.25. So our new current for the heater is 5.21 amps, and the salad shooter is 2.09 amps. So to be on the safe side, we're going to be using switches that are rated for 10 amps, just to be safe. And for our wires, we are going to be using 14 gauge wire because it's standard for 15 amp circuits, and we're only going to be at 5 amps really most of the time, so that should be good.
Hello, my name is Colton, and I'll be talking about some of the main design and material choice changes that will be for build 3 for the Fido build. So the first one is you're going to use a PBT filament. It's better for high temperature. It's also chemical resistant and can be food safe, especially if you injection mold it. That'll give us a better stability than using most any other filament. Additionally, we will have a uniform stainless steel body. Currently, it's like half stainless steel and half printed. We're going to make that more uniform all the way down, like all the other appliances you see on your counters, that they will match everything else and be fit with your ecosystem of your appliances. Additionally, we will add, instead of the fancy controller that control the temperature of the heater, it took too much time and it's a little bit too complicated. We're just going to have one or two buttons to turn on your grinder, to turn on your heater. You do not need it to be complicated. We don't need it to be overly complicated. It'll just be one button or two buttons. Also, we're still experimenting with the idea of a spatula that helps clean out the inside of the butter grinder to help make sure the butter falls out nicely. We're not entirely determined on if that is necessary, but we will experiment with the idea and work on it further to see if it is a viable option. Additionally, we'll be putting weights or just making the base heavier so it won't tip over as easy. Make it more professional feeling. Additionally, we'll make the logo not laser cut out of wood, but probably a sticker or etched into the stainless steel on the side. With these changes, it'll become less of a prototype and more of a final product that our customers would want and need.
Our last bill of materials, we only bought 4 things to incorporate in our last build. So filament for 3D printing, stainless steel metal plates for the casing, so it looks more professional looking, wire connector nuts and on and off switches that are round and black, with the mindset to look more professional and better looking.